Welcome. In this video, we'll look at using the definition of the derivative to calculate the derivative of a formula involving a square root. So let's start by defining our function that we're working with. We have a function, we'll name it f of x, but we could use a different name, that's equal to the square root of the quantity 2x minus 5. And we remember, when doing the definition of the derivative, that the derivative is defined by a limit as h goes to 0 of a difference quotient, which represents an average rate of change. That difference quotient, the average rate of change, is calculated by evaluating the function at a point x plus h and subtracting the function evaluated at x. That quantity will be the change in my function, and then I divide it by the change in x, and h. And so I'm going to use the formula for my f of x. Inside the formula, x appears once, so that when I calculate f using x plus h takes the place of that variable, and I get 2 times the quantity x plus h, then subtract 5. It's common to distribute out 2 times that sum, and so I'll write my function at x plus h as 2x plus 2h minus 5. The change in my function, which is measured by f of x plus h minus f of x, can now be written as the square root of the quantity 2x plus 2h minus 5 minus the square root of the quantity 2x minus 5. In my definition of the derivative, I'll need the difference quotient, the average rate of change, and that's given by f of x plus h minus f of x divided by h. That h comes from, if you took x plus h and subtracted x, the x's cancel and I get h. That's the change in my input variable. So this is my rate of change. So when I substitute in my square root formulas, I get the square root of 2x plus 2h minus 5 minus the square root of 2x minus 5 and divide it by h. That's my difference quotient. Now, in order to calculate the derivative, I'm going to need to take a limit as h goes to 0 of my difference quotient. And notice right now, if I divide it by h equals 0, I can't do that. This is an undefined value when h is 0. But notice that at the top, if h is 0, I get 2x minus 5 inside the square root minus the same thing. And so I have 0 divided by 0. That means that there's going to be a way to cancel the h. I need to find how to cancel the h. And so we're going to take a little pause now and talk about what can I do to rewrite that fraction so that I can cancel the h. How can we rewrite it? And the key idea is that we're going to use something called conjugates. And so I want to remind you of some basic facts that show up in algebra. If I take a number plus another number, and I multiply it by, so a plus b times a minus b, if I use FOIL to multiply that out, I get a squared for the first terms, a times negative b gives me minus ab for the outer terms, b times a gives me ab for the inner terms, and then I get minus b squared. And notice that the ab cancels. These two terms are conjugates to each other. When you multiply conjugates, you end up getting the square of the first term minus the square of the second term. So if I had a square root of a number, let's call it u, and I have, let's do subtraction first, because that's what we'll be looking at. If I were to multiply by the conjugate, square root of u plus the square root of w, because I'm squaring, I get the square root of u gets squared minus the square root of the other term, the w squared. And squaring cancels the effect of the square root, and I get u minus w. And so conjugates give me this tool to, when I multiply by a conjugate, I end up getting a square. So let's go back and see, what does this have to do with our problem? We have a square root of a formula minus the square root of another formula. And so I can create a conjugate, but if I'm simplifying a fraction, I can't just multiply the top by the conjugate. To leave it unchanged, I need to divide by the same thing. Multiply and divide by the same value. Those are inverse operations, and so they undo the effect. And so we're going to rewrite it as, we'll multiply by the conjugate on the top, and we'll divide by the conjugate on the bottom. And so it looks like we're getting more complicated as we go until we expand the conjugate multiplication. So when I multiply the conjugates, I get the first term in the square root gets squared, so the square root goes away. And then I subtract the second term in the square root is squared, and so the square root goes away. The numerator looks simpler. I still have an h, and don't forget that the denominator needs its conjugate, 2x plus 2h minus 5 in the square root plus square root of 2x minus 5. All right. Now we're going to leave the denominator alone. That's a pretty common theme in our derivatives. And simplify the numerator. So I get 2x plus 2h minus 5. Distribute the negative sign, I get minus 2x plus 5. And then the denominator is still the same. I have h times the conjugate term that we had. Things start to simplify. 2x minus 2x cancels, minus 5 plus 5 cancels, and I'm left with just 2h on the top divided by h and the conjugate. And notice now that we have this expanded and simplified the numerator, the h in the numerator and in the denominator now cancel. Times h divided by h, they cancel. And I have a simplified version of my difference quotient that no longer is dividing by h. And that's important because our limit definition for the derivative, we're going to be using h equals 0, and we don't want to have a divide by 0 in our problem. We now have a simplified formula for our average rate of change, and to finish the problem, we're going to take that formula we've just found and evaluate its limit as h goes to 0. Our derivative, f prime of x, is defined to be what we get when we take a limit as h goes to 0 of the average rate of change. And so we take a limit as h goes to 0, and we use the simplified formula for our average rate of change. So we get 2 divided by what turned out to be our conjugate term. And there's only one spot that h appears in our formula. So this h is going to get closer and closer to 0 until it goes away. And so our derivative is 2, set the h to 0, I get 2x plus 0 minus 5. And then I'll add the square root of 2x minus 5 in the denominator. And when I think about what adding 0 does, it doesn't do anything. These are the same term. So I have 2 divided by 2 square roots of 2x minus 5. Those 2's cancel, leaving a 1 in the numerator. And so I find that my derivative is 1 divided by the square root of 2x minus 5. So in a problem that involves the square root, when I set up my difference quotient, this difference of square roots is going to require using a conjugate, and I multiply and divide by the conjugate so that when I simplify, the square roots go away in the numerator, and I'm able to cancel that h that I can't divide by 0, so that I can evaluate my limit. And this is how we take a derivative of a formula algebraically that has a square root when I use the definition of the derivative.